Hi, I'm Dr. J. Glory, Associate Professor of Physics, Institute of Aeronautical Engineering. Today I wish to tell about the surface area and quantum confinement. So in this we are going to see the introduction, origin of nanotechnology, nanoscale, nanomaterials, significance of nanoparticles, that is why properties of nanoparticles are different when it is in compared to the bulk materials. That is why properties of nanoparticles is different compared to nano size. Then surface area, quantum confinement, and then we are going to see the references. So in the introduction part, in recent years, nanoscience and nanotechnology has become one of the most important and exciting fields in physics, biology, and engineering and technology. So generally, nanotechnology deals with the structure of size 100 nanometers or smaller, and it involves developing materials or devices within that size. So nanotechnology has the potential to create many new materials and devices with wide-ranging applications. So here, the nanotechnology used in medicine, electronics, and energy productions. So what is the origin of nanotechnology? Where it came from? In the American Physical Society meeting at Caltech, a talk was given by the physicist who is Richard Feynman. There is plenty of room at the bottom. It was the first use of the concepts in nanotechnology. So in the American Physical Society meeting, the physicist Richard Feynman talked about there's plenty of room at the bottom. So that is the first use of this concept in nanotechnology. So Feynman described a process by which the ability to manipulate individual atoms and molecules might be developed using one set of tools to build and operate another proportionally smaller set, so on down to the needed scale. So here he described a process. He described a process by which the ability to manipulate the individual atoms and molecules might be developed. So how he developed that manipulation is using one set of tools to build and operate another proportionally smaller set. So on down to the needed scale. Go on down to the needed scale. In the course of this, he noted scaling issues would arise from the changing magnitude of various phenomena. The changing magnitude of various phenomena, that is like gravity, would become less important. Surface tension and van der Waals attraction would become more important, etc. So he noted the scaling issues, that is when he is going down, when he is going to reduce the size for his needed scale, he noted the scaling issues. So he noted that scaling issues would arise from the changing of magnitude of various phenomena, like gravity would play a vital role, that is gravity would become less important, and surface tension and van der Waals attraction become more important, like that. The term nanotechnology was defined by the Tokyo Science University professor Norio Taniguchi in a paper as nanotechnology mainly consists of the process of separation, consolidation, and deformation of materials by one atom or by one molecule. So, the term nanotechnology was defined by the Tokyo Science University professor who is Norio Taniguchi in a paper. The definition is nanotechnology mainly consists of the processing of separation, consolidation and deformation of materials by one atom or by one molecule. So we are talking about the scale that is going down to the needed scale. In the first slide itself, we talked about go down to the needed scale. What is that scale down to the scale, needed scale? So here comes to the nanoscale. Nano means 10 power minus 9. Nano means 10 power minus 9. A nanometer is 1000 millionth of a meter. So that it is 10 power minus 9 meters. 1000 millionth of meter equals to 10 power minus 9 meters. So, atoms are extremely smaller and the diameter of a single atom can vary from 0.1 to 0.5 nanometers depending upon the type of the element. So, in the scale, atoms are extremely small and the diameter of a single atom can vary from 0.1 to 0.5 nanometers depending upon the type of the element. Suppose if you take an example, one carbon atom approximately have the diameter 0.15 nanometer. Water molecule is almost 0.3 nanometers across. For better understanding, the size of nano can be compared with others. A red blood cell is approximately 7000 nanometer wide. The human hair is about 80,000 nanometers. Here we can see clearly the scaling of different materials. That is, when the size of the bulk material reduces to nanoparticles, how the scaling is, how the material becomes. So when taking 1 centimeter, so that is tennis ball. So it is 1 centimeter, that is in terms of meters, the size is 10 power minus 2 meters. If we divide with 10, we'll get 10 power minus 3. And again if we divide with 10 meters, that is 10 power minus 3 divided by 10, that is 10 power minus 4. In this size, that is equals to 100 micrometers, is equals to the thickness of human hair. Then dividing with 10 meters, again 10 power minus 5 meters. At 10 power minus 5 meters, which is equals to 10 micrometers. 10 into 10 power, that is 1 into 10 power minus 5 meters. So, the size of the bacteria. Then, reducing the size by every division with 10 meters, the size of the bulk material goes to very smaller, that is it comes to bacterial size. Then 10 power minus 7, the size of viruses. Then 10 power minus 8 meters, we'll see DNA. And going down to 10 power minus 9, it gives molecules. You can see the size of the molecule. And 10 power minus 10 comes to the atom size. So, here we have size of the nanoparticles. Size of the nanoparticles. So what is nanomaterials? All the materials are composed of grains, which can in turn comprise many atoms. So grains comprise of many atoms. So a material consists of grains. So it composed of grains. So in turns it comprises many atoms. So the visibility of these grains depends on their size. Conventional materials have grains varying size from hundreds to microns to millimeters. Hundreds of microns to millimeters. The material possessing grains of size ranging from 1 to nanometer is known as nanomaterials. The materials possessing grains of size ranging from 1 nanometer to 100 nanometer termed as nanomaterials. So nanomaterials can be produced with different dimensionalities, that is one-dimensional nanomaterials, two-dimensional nanomaterials, and then three-dimensional nanomaterials. Coming to the one-dimensional nanomaterials, in these materials, grains will be layered in the form of multi-layers, such as thin films or surface coatings. In the two-dimensional nanomaterials, this consists of ultra-fine grains, layered over layered or buried layers which can include nanowires and nanotubes, becomes two-dimensional nanomaterials. In the three-dimensional nanomaterials, this consists of nanometer-sized grains. Nanometer-sized grains. Some of the examples are precipitates, colloids, and then quantum dots. You can take examples as nanometer-sized grains, which is in three-dimensional nanomaterials. The nanomaterials reduced to the nanoscale 1 to 100 nanometers shows different properties when compared to what they exhibit on a macro scale. Macro scale in the sense of bulk form. So the nanomaterials reduced to nanoscale of size 1 to 100 nanometers shows different properties compared to what they exhibit on macro scale. For example, opaque substance become transparent in sense of copper. Inert materials become catalysts in the case of platinum. Stable materials turn combustible in the case of aluminium. Solids change into liquids at room temperature, which is for gold. Insulators becomes conductors, as in the case of silicon. Then what is the significance of the nanoparticles? That is why the properties of nanoscaled materials are different. Why nanoparticles shows different properties? Why? So the properties are different on the nanoscale from those at the larger scale. So the properties are different on the nanoscale from those of the larger scale. The quantum mechanical and thermodynamical properties become important at nano level, which are not seen at microscopic level. After studying an individual molecule's properties, it can be put together in well-defined ways to produce new and amazing properties. So the science dealing with the materials of the nano world is an extension of the newer, more modern terms. So nanoscience is based on the facts that the properties of materials change with the function of physical dimensions of the materials. So the dimensions at which the changes in the properties of the materials are observed depend upon the specific material and the property in question, as well as on the three dimensions which are restricted in the real space. Actually, change in the properties of the materials in these confined spaces are due to the change in the electronic structure of the materials. So when coming to the bulk properties, the bulk properties of any material are merely the average of all the quantum forces affecting all the atoms. But on reducing the size of the material, averaging no longer holds. So that is the main thing. Bulk properties of any material merely the average of all quantum forces affecting all the atoms. But on reducing the size of the material, averaging no longer holds there. It is observed that the effect does not occur when it go for macro to micro dimensions. The properties of materials are different at nano level due to mainly two reasons. There are many reasons on there. The material properties may affect. So here, the properties of the materials are different at the main reasons. That is, increased surface area and then quantum confinement. Let's see what is the surface area and then quantum confinement. So let's see surface area. When a bulk material is reduced to the particles or smaller size, then the surface to volume ratio becomes very high. When a bulk material is reduced to the particles or smaller size, then the surface to volume ratio becomes very low. So thus, nanomaterials have a relatively large surface area. Nanomaterials have a relatively large surface area when compared with the same volume or same mass of the material produced in a large form. For example, for a sphere, spherical radius is r. The surface area is 4 pi r square. The volume of the sphere is 4 pi 3 pi r cube. So, taking the ratio of surface area to volume, it becomes 4 pi r square divided by 4 pi r cube by 3. So, 4 pi r square by 4 pi r square to 3 by 4 pi r cube. So, 4 pi and r square. So, 3 by r. So, the surface area to volume ratio is 3 by r. So, for nanospherical material, due to decrease in size r, the above ratio increases predominantly. So, due to decrement of the size r, the surface to volume ratio, due to decrease in size r, the ratio increases predominantly so that it shows different properties. Suppose let's take an example. If we take a cube, so for a cube, the surface area is 6 centimeters square. As we take a cube, so the surface area is 6a square. Later the area is 1 centimeter. So the surface area is equals to 6 into 1 centimeter square. So it is equals to 6 centimeters square. This is the surface area. When it is divided into 8 parts. When it is divided into 8 parts. So when it is divided into 8 parts, we'll get 2. So when it is divided into 8 pieces, so front 2 and then back. This. So 1, 2, 3, 4, 5, 6, 7 and 8. So when it is divided into 8 pieces, its surface area becomes 12 centimeters square. 12 centimeters square. Thus, when the given volume is divided into smaller pieces, the surface area increases. Suppose for 27 pieces, the cube is divided into 27 pieces, then the surface area becomes 18 centimeters square. So thus, we can find when the given volume is divided into smaller parts, surface area increases. When the given volume is divided into smaller parts, then the surface area will increases. So that nanoparticles have a greater surface area per volume compared to with the larger particles. Since growth and catalytic reactions occurs at surfaces. Growth and catalytic reactions, chemical reactions occur at surfaces. So this signifies nanoparticles will be much more reactive than the same mass of material made up of larger particles. So let we can see with some good diagram. So this is the figure which is related to the increase in surface area for a given volume. So here there is a cube which have the dimensions of 1 centimeter. 1 centimeter. So the surface area of the cube for the given dimension, for the given volume is 6 centimeter square. 6 centimeter square. That is 6 into, that is 6a square surface area, 6 into 1 centimeter. So 1 centimeter square will become 6 centimeter square. This is the surface area for this 1 centimeter cube. So the volume of the cube, the volume of the cube is 1 centimeter, that is a cube. Volume of the cube is equal to a cube. So it is equals to 1 centimeter cube. So 1 centimeter cube. So the ratio is 6:1. 6:1. Then coming to the second figure. So it has surface area. That is the cube is divided into 8 pieces. The cube is divided into 8 pieces. That is this is 1, 2, 3. This is the 4. The same like here. 5, 6, 7, and parallelly to downwards it's 8. So the cube is divided into 8 pieces. So here the surface area 6 surface area is equals to 6 into 2 centimeters square. So that is equals to 6 into 4 centimeters square. So 24 centimeters square. This is the surface area of this second figure. Coming to the volume is equals to A cube, that is equals to 2 centimeter whole power 3, 8 centimeter cube. Now the ratio is 24 by 8. It is equals to 3 by 1. So the ratio is 3:1. So comes to the third diagram. The cube has been divided into 27 pieces. 27 pieces. That is so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 15, 16, 17, 18, 19. Parallelly from downwards also we have. So that is downwards we have 9. So 9 cubes are there. So that totally it is divided into 27 pieces. 27 pieces. So the surface area is equals to 6 into the dimension is 3 centimeter square. So it is equals to 18 centimeter square. Sorry. Six into 9 centimeter square. So it is equals to 54 centimeter square. So when comes to the volume, so 3 centimeter whole cube, 27 centimeter cube. So comparing surface area to volume ratio, so it is 2:1. So when the given volume is divided into smaller parts, surface area is increasing. So here when dividing smaller parts, the same cube we have taken. So for one solid cube bulk particle, so have the surface area 6 but the volume is 1. So the surface area to volume ratio is 6:1. When compared to when coming to the reducing of the size of the particle material, that is when the same cube with the same volume when divided into 8 pieces, then the surface area is increased, that is 24 centimeter square, volume is 8 centimeter cube. When coming to the ratio, it is 3:1. And it is again divided into 27 pieces, then the surface area is 54 centimeter square and volume is 27 meter cube. So that is equals to 2:1 surface area to volume ratio. So that's why here when given volume is divided into smaller parts, the surface area is increasing. So that nanoparticles have a greater surface area per given volume compared to larger particles. So that it shows different properties. Next, coming to the quantum confinement. When atoms are isolated, the energy levels are discrete. When very large number of atoms are closely packed to form a solid, the energy levels split and form as energy bands. But nanomaterials have the intermediate stage. When considering the particles in a potential box problem, when the dimensions of such walls or boxes are of the order of de Broglie wavelength of electrons or mean free path of electrons, energy levels of the electrons change. So this effect is called quantum confinement. When the material is insignificantly small size, typically 10 nanometers or less, organization of energy levels into which electrons can climb or fall change. Specifically, the phenomena results from electrons and holes being squeezed into a dimension that approaches a critical quantum measurement into that is called the excited Bohr radius. The phenomena results from electrons and holes being squeezed into a dimension that approaches a critical quantum measurement called the excited Bohr radius. So these can affect the optical, electrical and magnetic behavior of the materials, particularly as the structure or particle size approaches the smaller end of the nanoscale. So let's see through the diagram. So when taking the quantum confinement of bulk materials. So taking bulk material to nano-sized particles. So this figure A shows that detailed about the quantum confinement effect where the band gap energy is larger upon the increase of quantum confinement. So when taking the taking the bulk material, so here the band gap is, so that is here the energy levels, the bands, that is this is conduction, valency band, and this is conduction band. So here the energy levels are overlapped in the valency band. Like here also the conduction band, different energy levels, they are close to each other. When reducing the size of the bulk material, so here the bandwidth, the energy levels are somewhat discrete energy levels. So here the width of the band gap is increases. It's coming to again reducing. So reducing to smaller particle, the band gap is increasing more and more. Increasing more and more, so that electrons which are here are confined, the electrons in the valency band are confined in between this energy levels. So when the electrons are confined, so the properties are different, it shows different properties. So here in this figure B, it is the figure which shows the dimensions of materials along with the different examples of dimensional materials. So in 0 dimension, or else if we take 1 dimension, 2 dimension, 3 dimension, I am showing that the first level as 0 dimension. So in 0 dimensions, so we can take examples are quantum dots. In 1 dimensional, we can take nanorods and nanowires. So the difference between these nanorods and nanowires is the ratio between the diameter and the length. So here the diameter is larger and the nanowire's diameter is less, but nanowire's length is larger. So the diameter is the diameter of the nanorod is greater value and length is less when compared to nanowire. So nanowires have less diameter and length is greater. So if we take in the two-dimensional, so nanoplatelet becomes nano sheets. So because of electrons, particles are confined in this energy levels so that it shows different properties. So as reduced from bulk size to nano size, the band gap between the connection band and the valency band becomes more and more. So that here the electrons are confined in the energy levels, different energy levels, so that it shows different properties such as electrical, mechanical, thermal, physical properties also. So that's why nanoparticles have different properties when compared to the bulk material. So the references for this topic: Engineering Physics by Tyagarajan K, Tata McGraw Education Private Limited, New Delhi. A textbook of Engineering Physics, M.N. Avadhanulu, P.G. Ksheerasagar, S. Chandan Company, New Delhi. And then Engineering Physics, Dr. M. Armugam, Anuradha Publications, Chennai. Engineering Physics, P.K. Palanisamy, 4th edition, SciTech Publications, Private Limited, Chennai. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.